Since the last class, we're only doing fun things today. I want to sketchily derive the essential singularity of the Kosterlitz-Sallis transition, which explains some thermodynamic observations. And we'll finish up with a little kind of quick sketch of how we can use renormalization group maybe outside of the context that we have in this class for some scaling forms of entanglement entropies. So let's do the KT stuff first. So we'll start from the Kosterlitz RG equations that I derived last time. Remember, y is related to the vortex fugacity. It's like e to the what's it called? Chemical potential for a vortex. Is that right? Y squared, right? Okay. And I drew the RG flows last time. Y is relevant above the Kosterlitz-Sallis transition and irrelevant below, for small y at least. Let's use these to examine some critical behavior. And I'm just going to sketch out a sort of quick argument for the scaling of the free energy that's, I'll say, consistent with these equations. Okay, so not a real derivation of the free energy, but we're just going to look at what this implies for the scaling of the free energy at Kosterlitz-Sallis. So we already know Kosterlitz-Sallis is sort of strange. It didn't come from long wavelength, you know, sort of actions and spin wave theory, if you will. But it came from the details of almost the microscopic physics, in the sense that it comes from this vortex binding unbinding. So we really don't know much about sort of the thermodynamics that induces. So let's just look in the vicinity of the Kosterlitz-Sallis critical point. And so this scaling variable x, I'm going to assume is small. So let's look near TKT. And we'll leave y the way it is. But I want to define what was my x before? Okay, I've divided it. Okay, so I want to use this for x. I'm going to call it x tilde, because this is what I was calling x by 2 previously. And I've set the coupling of the Hamiltonian to 1. Why did I divide x by 2? I guess it doesn't matter, but I want to expand one minus x, or 1 over 1 minus x for small x, because I'm in the vicinity of the critical point, right? So this is very close to 0. It's a very small parameter. Okay, then from that I can just rewrite the RG recursion relation. Like that. And so just from that simple transformation, And I'll keep y the same. It was 4, so I'm going to do that's x tilde now. That's just another form for the Clausewitz RG equations near TKT. Let's drop that tilde. And use, let's see, I want to get rid of the parameter L so that I can solve these equations. So use the chain rule. Just and you'll get something like you should get something like that. I've just rewritten the RG equations in terms of x squared and y squared. Okay, and then like good mathematicians, you can just divide this one by this one, and that cancels your DL. And so then you'll have dx squared over dy squared equals 4 pi squared. I think I forgot a y squared there somehow. This one has to be squared. Nice. Okay, that's some solid math. Now, what that is just an equation of basically hyperbolic trajectories. So if I draw this in x and y, I have these different hyperbola. I'm near Clausewitz-Sallis. X equals 0 is my transition. So if I'm below the transition, I'm in that algebraic quasi-long-range order phase down here. And now I have two special points in this equation, which are straight lines. Y equals x over 2 pi. Corresponding that c equals 0, and then y equals minus x over 2 pi. Okay, these flows will look like this, and these ones will go up. So it flows like that, and it flows like this. And then y is still relevant above the Clausewitz-Sallis transition. So this is the paramagnetic phase, which is flowing in this trivial fixed point way in the upper left. So in my equation, let's see, c is less than 0 here. No, so it's probably C greater than 0 here. C is less than 0 here. And this special line is, well, both of these lines are C equal to 0, right? So these hyperbola approach this critical line as C goes to 0. And when C changes sign, that constant of integration, when C changes sign, then the flows intersect on the y equals 0 axis at different values of x, right? So it's like you have this whole critical line, not a single critical point. And they do that at values x, C is less than 0, so it's minus root, I would say, absolute value of C. Right, so the less, wait, is that right? I think I got my sign of C wrong. X is minus C, so this is maybe these are backwards here. I don't know. Check it for me. So C in either case is just the distance from that point, right? So my C equals 0 line is here. And for finite C, I just move on this axis, away from that point. So I'm measuring the distance from that point. And I'm just going to assign it, if I'm sufficiently close, I don't know, the linear distance t minus tc, or tkt. Okay, so all I've done is, examine the flows of this equation and argue that C measures the distance from Costa Salis when so it doesn't, if I have a finite y, I flow to y equals 0, and then the distance from tkt is measured by C. Okay, so how do we use this to learn anything about the thermodynamics? So let's see if we can make an argument for how this affects the correlation length, this equation here. So it's come from let's come from below. Okay, I got to fix the sign of this. Oh, why did I change the signs of that? That was right? It's C less than 0. Hyperbola C less than intersect. Yeah, so it's here. These have to be less than 0. That makes sense. Sorry. I'm losing my mind. So then this is negative because of this negative sign, right? Make sense? Okay, so I want the case when C is less than 0. So I'm coming from TKT from below. So T less than TKT. C less than 0. B is just some parameter. Now I realize I use B for the scale factor, but it's too late now. So that's x squared. So I can take the derivative with respect to L, which I know from my RG equation. And I'll just substitute in b squared t minus tkt, like this, say. tkt. And then just integrate this to solve for, in this case, L. So this is just x squared plus a squared. Okay, so you just get an arc tan from that. That's the indefinite integral. It looks pretty useless. But you have limits on that integration in principle. So if you're integrating to obtain L, you can imagine x going from the critical point to the distance away from the critical point. And what we're going to do is integrate to the point where basically I'm no longer critical. So the point where the finite correlation length emerges. And then from the functional form of that finite correlation length, we'll argue, that determines essentially the free energy. So it's just kind of a length scale argument. So we have two limits of integration. I mean, x in principle can be anything on that line. But let's imagine integrating from, x equals 0 to the point where, like I say, we lose criticality. So I'll call it the point where perturbation theory breaks down. We're no longer near the critical point. And because x is a distance from that critical point, it's just anything that's order 1. So arctan 0 and arctan 1. And arctan 1 is just pi by 2 or something, right? Well, arctan infinity is pi by 2, so let's call it close enough. And we have what we've done is we've integrated to get, an L from an L initial to an L final or something like that. So this L, I'll label it L final, is then T minus TKT pi by 2, or whatever comes from that arctan. So it's just a matter of interpreting what this L is. Right? We've just done an integral. We have some limit on the integration. It's somehow related to TKT. So if you think about your correlation length, let's use this to define where the correlation length is basically becoming finite. And we want to measure the correlation length before any RG steps. Right? And this L is measuring, or is parameterizing the RG. Then this corresponds to so in a UV scale, or in the original microscopic scale, right? Because, well, would it be 1 over B? So then, different B, but then this would imply that somehow your correlation length in that scale is proportional, right, to, say, e to the L final in this case. Yep, e to the pi 4b root t minus t kt. Okay, so it's just a qualitative argument. So you basically don't care about this constant in front. I'm not even sure I got it right. But the functional dependence of the correlation length is, this turns out to be what it is. And so it's not an exponential, and it's not a power law decay. I mean, it's e to the 1 over the distance from the critical. And that's the correlation length. This isn't any argument about the 2-point function. We're just saying that there's a length scale that corresponds to the breakdown of this perturbative analysis where you've left the critical regime. So I think most interestingly, so it doesn't, by this argument, it doesn't look critical in that sense. And you got to believe somehow that you can, okay, so this is the conceptual kind of jump here, is that the correlation length is this exponentiated length scale. So it's pretty hand-wavy, extremely hand-wavy. Once you have this, you can say there's a free energy. Okay, so consider that. I'll just write in terms of the distance, t minus tkt, t minus tkt. Our old expression that we've seen 100 times. And let me rewrite, let's see. I know that t, oh yeah, I can write this in terms of the divergence of t in terms of mu. So I know that yt is related to 1 over, nu. So let me write this like b over t to the minus nu. And because that's 1 over yt, This is also going to be very qualitative here. I just want to write this as, I've now written this as B over correlation length. So I can eliminate that. And I'm just arguing for basically the scaling factor out front of this is where the functional dependence lies. So that's B over the correlation length. And whatever that is, who cares? It's still just some function of, you know, a finite correlation length and a finite number B that is the scale factor of the RG. So that can be, that's some number. You can set them to be the same if you want, so that thing could be order 1. For example, and then you could argue that B goes as the correlation length up to some unimportant factors. You're just interested in the functional form. So that would mean the free energy should depend on small t, like correlation length minus d, g, whatever, order 1. I don't even know if that's an equation. Minus, so it's minus some constant over t minus t kt. Oh yeah, and d is 2 here. I just use the general expression, but remember this is 2dO2. It doesn't get any more sketchy than that, but that is the actual functional dependence of the free energy as you approach a transition. Okay, so we could have done that properly, but you'll get the same thing. So all the derivatives of the free energy are finite. That's what's different between what we talked about at the start of class. So that's basically the reason that the Kosterlitz-Salas transition is hard to see. Okay? It comes from this argument. It basically comes from this functional form. So that's called an essential singularity in the literature. Essential singularity in the free energy, all derivatives. So remember I talked about that classification, first order versus second order, based on which derivatives you have in the free energy, which ones are singular, say. So Kosterlitz-Salas is like infinite order. So it's like an infinite order transition. Nobody calls it that. So it's continuous in some sense, because it's not. So basically, you're either first order or you're not first order. And this is a continuous transition with an essential singularity. And you can never get a singularity in any sort of thermodynamic quantity that's based on the free energy because of this form. So like the specific heat, kind of the quintessential bulk measurement. There's no exponents associated with that. So it's basically unobservable experimentally from these bulk measurements. That's why it was so hard to find, I guess, in some sense. That's why you need to use this crazy stuff like superfluid density fractions in these torsional oscillators to see the Kosterlitz-Thouless transition. If you just took a two-dimensional Mylar sheet and absorbed helium on it, put it in a dilution refrigerator, cooled it down, you would see some sort of features in the specific heats, but you would never see anything that corresponds to, say, like the lambda transition in 3D, which is very clear in the specific heat. Okay, so if you do your
one step of your derivation of free energy.
derivation. Yep.
So you used eta is proportional to t to the minus nu in the second line. So
What line? Second line here?
yeah, yes, you replace t to the minus nu with correlation length.
Yeah.
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 But
Yeah.
but we define.
But this is the expression for the correlation. Hey, man, don't pick it apart. It's definitely not correct in some rigorous sense. I mean, that would be assigning something crazy to nu. You know, just, that exponent doesn't exist. So I have no defense for that. You can do this properly. It takes a lot longer than half an hour.
People chat.
Yeah. I mean, this is the right form here for the free energy. Yeah, don't just trust me. Any other questions about Kosterlitz-Thouless? We could have a whole class on Kosterlitz-Thouless, and you know it leads into like Haldane physics. You know, we can do the quantum version that would give you. You can start with gaps in spin 1, Haldane chains, and relate this to topological features. And of course, there's a whole field of modern condensed matter that deals with topology and topological phase transitions and topological order and everything like that. So, unfortunately, we don't have that class here. But hopefully this is motivation at least that there's some interesting new physics that comes out of topology. You know, it's kind of outside of this. I taught this class in this kind of conventional framework. Remember, it was almost like you start doing perturbation theory. You know, mean field theory is kind of the zero order perturbation theory. And then you develop that perturbation theory, and in the Landau framework, you show that there's some problem with that. It breaks down. So the RG is a completely different way of looking at things. So in terms of rescaling and renormalizing. And so most of the class we spent on renormalization group theory, you know, and the consequences that gives you. And then this Kosterlitz-Thouless is outside of that long wavelength RG theory because it has to do with topological objects. So it's even a step beyond that in terms of breaking convention. But once you understand it, you can create these kind of like RG arguments. Like you can understand it in terms of a renormalization group, but it's just a little different. You need these fugacities and all this type of stuff. But you know, now this is a fairly well-developed theory, of course. So I just want to do one fun thing before we finish this class, and that's to use everything we've learned about RG to basically derive some forms for scaling relationships for things we encounter in quantum systems. Okay, so everything's classical in this class. And if you take 733 with me next year, we do quantum many-body physics. So it's essentially we're doing the path integral. It's all about path integrals. And we don't talk about the RG there, but some of the motivation behind why these path integrals are interesting lies in this fact that you can write a path integral in such a way that it's maybe universal or describes a critical point. So that's a whole class on quantum many-body physics and you know, bosons, fermions, spin path integrals, Berry phases, all that type of stuff. But let's just say one note about something fun in quantum mechanics. And we'll use our classical scaling intuition to derive a scaling theory for the entanglement entropy. So, I'll say entanglement scaling at a, so it's a critical point, but somehow it has to be quantum. Critical point from the RG. Okay, some of you are working on entanglement, so this is just kind of a philosophy about what happens at critical points. So to be concrete, let's imagine we have some quantum state, like a singlet. And I can divide my system, so here's two spins, spin 1/2. And I have a pure state that I'm asking how are these two components of it entangled. And by two components, I'm going to label them A and B. Maybe they're separated spatially or something like that, prepared in this state. Whatever. I want to do that, you know, I want to answer that question by studying the entanglement entropy. Where generally the entropy is defined, this is like your classical Shannon entropy. Instead of classical probabilities, you have a reduced density matrix. So region A could be, generally, it could be something bigger. I can imagine A and B. In this case, A is just one spin and B is just one spin. So in that singlet case, the entanglement entropy is log 2. So it tells you it's maximally entangled. If it was in a product state, compared to the product state, okay, so what I want to do is take this intuition. You know, I have a single entangled, okay, singlet, and scale it up to the thermodynamic limit, like what we always consider in this class, and ask, how does the entanglement entropy of a many-body quantum system sort of scale as we go to the thermodynamic limit? And by scaling, we mean with the size of region A. Okay. So it's generally a very hard question. You know, it actually depends on a lot of details of the state that you prepare, how quantum it is. So let's just take a very idealized system. And the intuition we should have in this class is that We can either be critical or not critical. And if we're not critical, then we have a length scale. Okay? So that's case 1 maybe. So the correlation length is finite. And it just makes sense, kind of intuitively, that your entanglement, or the range of your entanglement, might follow, or might be locked somehow to that correlation length. So if I had a 2D system with a region A and a region B, and I have some sort of correlation length, that's my characteristic length scale. Let's just tie that correlation length to the range of, imagine we have a bunch of singlets in that system. So maybe it's a many-body system, we have a bunch of singlets in there. And after you get over the correlation length, there's no more singlets that occur at that length scale. So it's kind of like a cutoff for your entanglement. And the question we're asking is, what's the entanglement entropy, which quantifies the entanglement between 2 regions? So if I have singlets out here of this size, who cares, right? When you perform that partial trace, they're not telling you about the relationship between A and B. But if I have singlets that cross the boundary, all sorts of different length scales, they can be very short, and they can be long up to that correlation length, then those will entangle A and B and give you contributions to the entanglement entropy. And so generally there's a region around that boundary, which is kind of local to that boundary, where all the entanglement occurs. Okay, and you get 1 contribution to your entropy from every single singlet. And this gives us kind of a heuristic notion of the area law. And that term area comes from thinking about this in 3D. It comes from black holes and all this Bekenstein, whatever it's called, Hawking stuff. So if you had a sphere for your entangling region, you're entangling, your region A, your entangled region, then if you scaled that sphere bigger and bigger, the entanglement entropy would just scale as that boundary, which is an area in 3D. So in here it's just a line, but we use the same terminology. So entanglement entropy scales as the size of the boundary, which some people call dA. Whatever. That's fine. You can build a whole career off of studying area laws. But what happens at criticality? Okay, I want to move away from a gap system to a system where the gap closes. And this kind of heuristic, this idea that makes sense that you have a length scale is gone. So that's the case that's interesting for this class. Oh man. So the correlation length goes to infinity. So there's no length scale. So how does the entanglement entropy now scale with that boundary? You want to make a guess? I mean, it would almost make sense that you could have, singlets now that span from the bulk, right? Bulk to bulk. So the idea is that we have these contributions at small length scales, but also large length scales. So you can almost imagine that you have a volume contribution. it's feasible anyway. It's like when you thermally mix these things, they pick up volume contributions. So you can entangle the entire part of the entire bulk. But that's not what happens. And so that's what we're going to show. So let me keep this as sort of a postulate. The idea that, you know, we have entanglement that comes from contributions local to the boundary, but now there's no cutoff for that. Okay, so I can call those postulates, or I don't know. Sure, why not? Then I don't have to justify them. Okay, so S, the entanglement entry, comes from contributions local to the boundary. But since there's no length scale, you have to ask what local means. And so what local will mean for us is, you know, it picks up contributions equally at every length scale. So every length scale in an RG sense. So what that means is we're going to have to integrate. We're going to have to integrate over all of the length scales. Because we're assuming we have small local singlets. We have singlets, you know, at every single, you know, b to the n, if you want to call it that. So how does that look? Let me do an example. In one space point, which is a 1 + 1 CFT. And let me imagine I have a system of 8 spin 1/2 spins sitting on a lattice. And let me divide this up so that region A is over here and region B is over here. And I want to ask, what's my entanglement entropy in terms of the size of, say, region A? And I need contributions local to the boundary only. So I'm going to do an RG calculation with some arbitrary scale factor that I'll set to 2. Okay, and so this would be n equals, you know, so my, you know, my R, let's call it R, which is the length scale that I'm measuring lengths in, is something like A, B to the n, where A is my, you know, this is my A here. Let me call it delta. And I'll set delta equals 1 mostly. And then n is 0 for the first length scale. And so I imagine I have singlets at that length scale, and I only want to look at the ones local. So the ones local to the boundary. So the shortest distance at that boundary. So I can imagine a singlet that looks like this. And I can imagine getting an entanglement contribution. So say S, I don't know, S at n equals 0. Is that what I'm doing here? Is some sort of, whatever, it's log 2, or it's something reduced from log 2, it doesn't matter what it is. So let me actually keep drawing below here. So now let me perform an RG step. And let's look at locality at that next step in the RG. So this is my block spin now, whatever it is. I got one from there, one from there, one from there, one from there. Okay, so from my postulate 1, again, I only want to look at contributions local to that boundary. So I'm looking at that contribution. So it's also order 1 there. Now that's at the next RG step. And the next RG step, you have an order 1 contribution. Sn equals 2, equals order 1. So that's all postulate 1. And then postulate 2 says I keep iterating to infinity. I ran out of lattice sites, so I've already iterated to infinity. And I add contributions. I sum contributions. And it just happened, you got to think about that a bit, but entanglement entropy is the right quantity to sum these things. So my total entropy is 1 plus 1 plus 1, which isn't 3. It's like log of 8 spins, but log of base 2, because that's my B, right? So it's basically log L. And that's the correct form for the entanglement entropy of a 1D critical system. It violates the area law. Because what the area law is in 1 dimensions would just be like this. Just be the first step here. There's some local spins, or maybe they're not just nearest neighbor, but there's some range corresponding to the correlation length. And that's just order 0, that boundary. Or sorry, length 0. It's just a point. So this is a violation. So it's like I said, it's almost like you're violating the area law by picking up bulk contributions. But in this case, it's not a volume, it's a log of the volume. Let's formalize this argument a bit more. The point is to show you that log. When you're integrating over RG scales, RG length scales, then that log is the measure of integration. That's what this tells you. So remember, this is something like e to the n, I'll call it L. What did I just write here? E to the n. This is my infinitesimal parameter. This is the quantity that I use to develop the differential equations for the RG. And so this is the total time, or the running time, or whatever you want to call it, after n RG steps. So if just like I use that for my differential equation, it's that I integrate over, basically. So R is my kind of length scale. It's what I'm measuring length in. So what I need to do is basically take D log of R. So that's the measure of integration. And if I go back to this 1D example, what is that integral? So the thing that I just kind of did with that discrete sum, it's the integral from R UV, call it, to R, I don't know, I'm going to call it IR, D log R. And my RUV is just delta, because it's when B, it's like when n is equal to 0. Yeah, okay. Where RUV is delta. And the IR cutoff, well, it's different things. Depends if you have a length scale or not. I mean, where do you cut off this integral? You're trying to figure out, again, in some sense, you know, how much this region is entangled with the rest of the system. So if there's a correlation length, you just cut off that integral at the correlation length. But if there's not a correlation length, then the next length scale is the full length of that, or the length scale corresponding to that system. So the IR cutoff is just the min of the correlation length, or L, where this is the characteristic size of region A. So then you get this log violation. You know, in 1D, if RIR is equal to L, then you get something that's like, you know, log R over log delta or something like that. So critical. Log L over delta. And things are not universal when they contain the UV cutoff. That's the point with the exponents. The critical exponents, there was no A or no delta or whatever we're calling it, right? But in the case of this log, you know, luckily you get log L minus log the cutoff. And what happens is the coefficient of that thing is a universal number. So plus order 1 terms. So this is the central charge of the CFT. So if you take CFTs, you'll see the central charge. If the upper cutoff was just the correlation length, then this first term is just log of some constant, right? So you just get some constant. So when it's gapped, or not critical, log of a constant equals a constant. So that's the area law. So this logarithmic measure works in 1D. Therefore, I blindly follow my postulates, believing they're true in any dimension. And so let's do that and see what happens. Okay, so D greater than 1. Now the geometry of the boundary comes in, but let's just take a simple case of a flat boundary. So we can imagine in 2D, can't believe I'm doing this. I'm missing one. So let me make a flat boundary. I've cut a 2D system in half, and I've made it region A on the whatever left and B on the right. Okay, so I'm just going to do the entropy contribution at all length scales. So at order, so what is it called? N equals 0. These are my singlets here. And there's L of them, which is the length of my boundary. All right? I'm erasing those. Let me do an RG step. So I'm going to make block spins. B equals 2 in 2 dimensions. Oops, I'm out of spins. Okay, I made block spins. Now I'm entangling those locally. So this one gets entangled with this one. So this is L by 2. And if I do it again, right, the next RG step takes this big thing here, makes a block out of it. Then you'll see I'll get L by 4, L by 8. That's a geometric series. It equals L. So this gives me 2L, which is just a constant factor times the boundary length dA. Right? So it's proportional to, so you still get the area law. I don't know why I put that in quotes. Let's do the integral. That's just the counting argument. Flat boundary, it looks like, of course, that's D equals 2. Oops, D equals 2, big D. So what it looks like is I'm doing that integral, but inside that integral, I have the length, L, measured in units of R. So what this means is ds over the measure d log R. The thing I'm integrating is the length of the boundary in the right, units for that scale transformation or that coarse graining, which is R. And I can generalize this by just putting a d minus 1 here. Now I hate big D, so I'm using small d. And that's what each one of these things is here. It's L over R at every length scale. So let's just do the integral in general dimensions. So for general D, so I'm integrating, I'll do cutoff, I'll keep it critical, so I'm at L, L to D minus 1. Okay, the issue is that the measure, D log, okay, so D log R is just dr over R. So let me do it like this, L over R, D minus 1, D log R, integral L to the D minus 1, 1 over R to the D minus 1, dr over R. Okay, so let's just do the integral. Pull that L to the D minus 1 out. So I have 1 over R to the D, which integrates to 1 over R to the D minus 1. Evaluate at the endpoints. I can write this like this. I've just done that carefully. So from the lower boundary, lower limit of integration, I get L over the cutoff to the D minus 1. And then I basically have order 1 contributions after that. And you have some constants out front. So what you would call this is L over delta to the D minus 1 plus order 1 contributions. And that's still the area law. That's what we found right here in 2D. This is why the area law is non-universal, because it's always polluted by the cutoff. So whatever this is, this C naught, if I had a flat boundary, it's this. You can't see it because, you have ambiguity in terms of this cutoff. The UV physics pollutes, everything you want to do. So there's no universality here. Unlike 1D. 1D you have something, the coefficient of this thing, because there's no cutoff there, gives you some universal number. It's like a critical exponent, but not, it's just not an exponent. Question?
Yeah, I'm just a bit confused about L. So you say it's the characteristic side with A. Is that
right?
The area or the region A?
Yeah, so, you have some A and there's some L. And so it can be if it's a circle, it could be the circumference. It's just related, by constants to any other characteristic length scale. So it's the dimension that matters somehow.
But we cannot say it's proportional to the square root of the area, the slim side.
L is the size. Oh, you're asking whether or not it's like. Okay, so if you had a square like this, L by L, say, it's L, right? Yeah, I don't know another way to say it.
This would be the entire system instead of just, you say, we split it up into region A and region B, right?
Yeah. So the idea is region B is infinite, and region A is something that I'm scaling.
Okay.
And there's some length scale of that system. There is no length scale in this system besides that. It's like, this is different than this is different than what we've done because there's a geometry, the entanglement depends on the geometry of the entangling region. So you're defining a length scale and asking how is that length scale entangled with the rest of the system. So that's why this integral has a cutoff that's not infinity. So and the L, I think this is what you're aiming for. This defines what L is, or maybe this defines what you're thinking about of L being in any dimension. This is the idea that you have a flat boundary and L is the length scale of that boundary, like this. Okay. There's no universal numbers when your boundary is flat. That's something that this tells you. But if you don't have flat boundaries, then you can get universal numbers in the entanglement entropy. So this is for D greater, there's no interesting geometries in 1D. This is for D greater than 1. So for example, if I had a sharp corner between A and B, then the geometry is what I put in the argument of that integral. Or I could have a curved boundary between A and B. So generally, I would write ds over d log r as something to do with this geometrical quantity. Okay, so in the flat case, it was L over R. Generally what you want is some integral over the surface, by some local geometric quantity that you're integrating over the surface, like the curvature of that surface, say, and the dimensionless differential surface element. So let me just write that. And what do I want? D sigma is, so it'll be dimensionless. So ds is dimension full. So r to the d minus 1. Dimension full. D minus 1 surface element. There's other ways of doing this. This is actually Lauren Hayward's way of doing this, which I like. What does that mean? What does all this mean? If you have a flat boundary, then that local geometric quantity is just a constant. Nothing's changing over that boundary. So just put G is C naught. And then, this integral on the right-hand side turns into something like that. Well, so it's then that divided by this, and that gives you that flat boundary. Because that's a surface. It's just like what we did here in 2D. But so generally, you can have curvature corrections. By the way, if you just have a sharp corner, so if you only had order 1 contributions at every length scale, you get a logarithm again. So imagine if I had a sharp corner here, somehow. I would have the area law from the 2 pieces, but then this thing looks the same at every length scale. There's only 1 corner. 1 corner here, 1 corner at the next length scale, 1 corner at the next length scale. So by the same argument, you would just get a log. It's like there's just a constant, total constant in that integral. So that's a good exercise. So we'll say sharp corner. So then S is, you would actually get the area law, L over R to the D minus 1, and then plus log L. And because you have a log L, it's actually log L over delta, but the delta factors out or whatever. Then you would get a universal number in front here. That's independent of the cutoff. Okay, one more fun example. So this one comes from, basically comes from field theory, but. So that universal number, say the one characterizing that log, that's not well understood. It hasn't been calculated, for example, in the epsilon expansion yet. In principle, it could be done. But let's look at the general structure of what's called UV divergences in field theories in the entanglement entropy for a curved surface. Okay. So imagine a hypersphere. So there's some curved boundary, and it's big, and it has a radius of curvature, I don't know. I think if it's coming from the other direction, it's minus r. Depends how you define that. So there's some preferential direction for this curvature. And let me just, I'm going to expand in that curvature, but I'm going to do it under a constraint. So let me define kappa is 1 over the radius of curvature. So I'm just going to call that the curvature. And I want to expand in powers of kappa. R is very big, so kappa is small. Why not? But I have to do it under a constraint. And this is a common constraint when you're considering entanglement. And that's that the entropy of A, so this is region A, is equal to the entropy of B. So I'm not proving this constraint. This is just a constraint on entanglement entropies in pure states, for 4 pure states. It means it's like, if all you care about is how A is entangled with B, then that should be the same as how B is entangled with A. It's just symmetry of that quantity, essentially. But, that means if I expand it in powers of negative curvature, I got to get the same answer. So I have to have only even powers. So my local geometric quantity that I have to integrate over it's like I'm doing an expansion. So there's my flat boundary, and then the next term I'll call C1. And that's my lowest order, which is R, 1 over R squared, but I'm going to measure it in units of, in the proper dimensionless units. So it's small r over big R, which I'm just going to call L squared. Plus C2 R over L 4. Yeah, well, that's ugly. Okay, so that's just saying that L is like R. That tells you a lot. This will tell you, in general dimensions, now you can calculate sort of the structure of divergences, if you will, in the entanglement entropy, just from this geometric, just from this local geometric quantity and this constraint on this expansion. So you can do this yourself, it's easy. 2 plus 1. C naught L over R plus C1, yeah. Now it's R over L plus C2, R3 over L3. Remember, your limits of integration are the UV cutoff and then just L. So you're going to get terms that are like L over L, but you're also going to get terms that are like L over delta, right? And all these other terms. So this whole thing, area law, maybe minus, I don't know. And you'll get these terms that are like C naught plus C1 plus C2. So you get you get the area law piece. Then you get basically, I would call these finite size corrections in the region L. That decrease in magnitude because L gets bigger and bigger. And then you get all these constant terms. And actually those constant terms don't have the cutoff. And in principle, they can be universal. So for those of you that study this stuff, if you add all of these up for a circular boundary in 2 plus 1, those are the F from the F theorem. So it's like S goes as C naught L over delta, maybe minus F. And F is something people try to calculate. It's believed to constrain or provide constraints on your direction of your RG flows. So again, if I had more time, we could talk about that. But there's theorems that the magnitude of F tells you, if you look at two fixed points and you want to know how they're connected with an RG flow, they go from larger to smaller always. Let's do 3 plus 1. I'm putting plus 1 because it's quantum, so this is just strictly 2 spatial dimensions. So 3 plus 1 means 3 spatial dimensions. A sphere. Okay, so, I mean, I don't know if you want me to do it all, but the only interesting structure is the fact that you have before you do the geometric integral, you have this C1 by itself now. And when you do the integral, that'll give you a log. So this implies that S equals C naught over 2 L plus C1 log L minus, and then all the sort of C2 over 2 and all the constants. So this is usual what I would call finite size scaling terms that go to 0 as L goes to infinity. And you have some constants here. But importantly, your C1, which is the coefficient here, is a number which can be determined through scaling. So if you have a sphere and you can calculate the area law to high accuracy, then you can fit out the subleading logarithm, and that coefficient is a universal number. So that's what's sometimes called A, Ricardi's A theorem. Small a. So for superfluid helium, this is interesting. So if you imagine you have superfluid helium at the lambda transition, no, even forget the lambda transition. If you just cool superfluid helium into its ground state, you calculate the area law piece, you get something that's non-universal, but you know you have Goldstone modes. And those Goldstone modes are described by a Gaussian theory. So what you should be able to do is measure for the Goldstone bosons, basically these subleading corrections. And you can compare, C1 to the free Gaussian theory. So you can make predictions on experiments from these simple scaling arguments. And so in high energy theory, they look at higher dimensions. So the general structure of UV divergences in the entanglement entropy just looks like looks like something where you get a logarithm in odd spatial dimensions only. And again, comes from this constraint on the curvature. So you get S, C naught, L, D minus 1, decreasing in powers of 2, plus log for odd dimensions only plus constants. Odd dimensions only. Okay, so that's something that Zamolodchikov and Solodukin and others noticed, I think, years ago in the context of field theory. Okay, so that's not on the exam, but this is an interesting, I think, example of how we can use very simple RG scaling and a couple postulates, just kind of intuitive postulates about entanglement entropy to really derive all the structure of at least the functional form of scaling in some quantum field theories. So as far as I know, whatever you derive via this argument, as long as your curvature is extrinsic, is the correct functional form for entanglement entropy. I don't know any exceptions to this argument. And so again, it's a simple way of seeing where universal numbers basically can come from. And again, it's the same idea of universality that we've always considered in this class. It's like the exponents, right? They're numbers that don't depend on kind of the details of your interactions, which means the details of, in this case, the UV physics, which is where your Hamiltonian is defined in principle. So you can measure the entanglement entropy on a transverse field Ising model or anything else in the same universality class. Then you expect, for example, the coefficients of these logs or these constants to be the same. They're universal numbers that go between, that just kind of transcend all sorts of different theories. Oh yeah, I could teach a whole class on entanglement entropy, but that class doesn't exist. So that's it for us. Any questions on this course? Or what I expect out of you in terms of your computational assignment? How's that going, by the way? I think the 10th is when I need everything. Okay? It gives me a week to mark. So if you don't see me around, put everything in my mailbox down here. And if you want to do the computational assignment, like digitally or whatever, just email it to me. So email me your, if you want to print off something for me to mark by hand, I'm happy with that. But if you just want to email it, that's fine. Email me your, whatever your code is. You just zip it all in a tarball or something like that. And then your project report is a PDF, and I'll mark it on my iPad. Okay, thanks for a good time. See you guys around.